All right, the screencast is going to be on current, voltage, and resistance as we continue studying series circuits. We're going to be applying Ohm's law, where voltage equals current times resistance, where V is voltage, I is current, and R is resistance. So here's the equation you're going to need to get used to seeing. If we review electrostatics, electrostatics was involving charges that were not moving, right? So it's going to be different now as we study electricity. But charge on an object that is static means it is not moving. And we said that they're either positive or negative, and that dictates the direction of the forces that are acting, right? Likes repel and opposites attract. So these objects have either positive or negative charge. That an object with a negative charge can exert a force on an object, just like polarization where the balloon sticks to the wall, right? And the force that is created, is really applicable to Coulomb's law, because if this has a negative charge, right, charge of one object, it'll repel the electrons in the wall, therefore it'll be attracted to the slightly temporarily positive wall surface itself. So that creates an attraction force, so the balloon stays on the wall. In the last concept we studied were the three ways we charged an object in class. One was charging by friction, then we could charge an object by contact if we touched that to another object, and the last one we could actually charge by induction, where we actually have an electroscope gain a net charge by the removal of electrons. But now we're studying electric current. And current is the movement of electric charge, or the flow of charge. And I'll typically refer to it as the flow of charge. Charges are going to be in motion. Where current flows when free-flowing electrons move. And the electrons are typically referred to or found within the conductors, the metal, often copper, within the wire itself. And the insulator would, let's just say it doesn't allow for electrons to move. And that's why copper wires are surrounded by a rubber or a plastic insulator. Current, I, right, is a symbol, and is measured in amperes or amps, letter A. So which way does current flow? Well, there's the idea, Ben Franklin developed the idea of positive and negative sides, positive and negative charges, actually. So we define that as positive and negative sides of a battery, and we call this the cathode, we call this the anode, and we say current travels from cathode to anode. But electrons actually move from anode to cathode, so they move in different directions. So even though current flows from cathode to anode, even though the direction with the electrons move is negative, or anode to cathode. So why does current flow? Well, current only flows when there's a difference in energy between the 2 points in a circuit. Just as water flows downhill from high gravitational PE to low gravitational PE, we can say that within a battery, current flows from high electrical PE to low electrical PE. So when I look at this and apply this, I want to make sure we get that current is what does damage. Current kills. Current does damage. Where you can feel something at 1,000th of an ampere, pain would be roughly 0.005 or 5,000ths of an ampere. And when we use the Van de Graaff, it's kind of somewhere in between here, roughly about 0.003 or 3,000th of an ampere. 0.01, involuntary muscle contractions, right? These are called spasms. You can have loss of muscle control, and if it's serious enough or long enough of time, you can do some serious damage to the entire body. But it's current that does damage, not voltage. So here I can look at the current in an outlet is able to be pushed, right? This is what's pushing the current, and it does damage to your own electrical circuitry, right? Your body. So that's why anything electrical around a bathtub is very, very dangerous. So you might ask, well, why is it unharmed? Well, the bird can stand harmlessly on one wire of high potential, but it better not grab a neighboring wire. Here's why. Because this is, even though it's high over here, it's the same height over here. So there's no difference, there's no differential. So there's no electric potential, right? There's no difference between them when the bird's feet are on the wire. Therefore, it cannot push current through the bird. So voltage. So voltage measures the difference in electrical potential energy between 2 points in a circuit. You can think of this like measuring the difference in gravitational PE. So voltage, or electrical potential energy, is measured in volts. And the difference in voltage is required for current to flow, which means that there's energy to do work. So if I look at this difference, creating a difference in voltage, a battery uses chemical energy to create a voltage difference between its two terminals, right? Cathode, anode. And it's delivering this current to, in this case, a resistor, or the battery itself, or the bulb itself, excuse me. and this is what we see then heating up, and then it emits light. So we have this current that's being pushed from a high potential to a low potential. And so therefore voltage we can look at like what we studied in class. If I've had water in this pipe, there's no height to it, so it can't flow. So here there's no voltage, there's no charges flowing, so the bulb is not on. But as soon as I lift this, right, we could say this is a higher gravitational potential energy, high to low, it's going to direct the current of water. Here's my high, here's my low, it's going to direct the electron, or in this case, excuse me, the current, we're defining it as current, it's going to be pushing current from high to low. So current flows in a circuit because a battery creates a voltage difference. So physicists, well, they weren't exactly wrong. It just depends on who you ask. A picture that a chemist versus a physicist, you know, they define it differently. That current's flowing from cathode to anode, where electrons are moving from anode. So when comparing the conventional to the modern electron flow, conventional is simply saying that it moves from, or current moves from cathode to anode, in this case it would be clockwise, where the modern electron flow is referred to as moving from anode to cathode, so that's just from like a counterclockwise position. So what is resistance? Well, resistance is a measure of how strongly a wire or another object resists current flowing through it. Resistance, capital R, is measured in ohms by the symbol, Greek symbol omega. So think of the relationship between resistance and current like water flowing from a bottle, right? The relationship is inverse. Voltage equals current times resistance, right? Ohm's law. By doubling the resistance, if I have twice the resistance here, one has half the current. So if I have twice the resistance here, only half of the amount of water is going to flow through here. Therefore, if I have half the resistance, in this example here, I would have twice the current. So we're using the amount of water flowing out of those containers as an example. So currents and resistance. So let's say I have this light bulb, I have a bulb here, and I have a 1.5 volt battery. That's my voltage here. It's pushing current through here. So one bulb has single resistance, it has full current. If I have two bulbs, it has twice the resistance, it has half the current. And we would see these bulbs getting dimmer. And if I added yet another bulb, I'd be increasing my resistance, right? 3 bulbs, 3 times the resistance, 1/3 of the current, or 1/3 of the current that would be in my example scenario here. So the brightness of a bulb is a visual cue. Key word here. We can see it, visual cue, as the current flowing. If the light is on, the circuit is closed and the current is flowing. When the bulb is bright, current is high. When the bulb is dim, the current is low. So materials that current can flow through. Conductors. These are where currents pass easily through them. Electrons flow very freely, right? The valence electrons we referred to when we studied atomic structure. The following materials have very low resistance, right? Metals, copper, aluminum, gold, silver. These are the metals that comprise wires or any type of electrical conduit systems. Semiconductors, they have some resistance. Silicon, these are what are used in computer chips, right? Silicon Valley kind of made silicon computer chips, kind of put them in the limelight. So materials that cannot have current flow through them, these are called insulators. Current does not easily pass through these materials. These block the flow of current. Electrons do not flow freely, and they have a very high resistance. Example, rubber, glass, and wood. So let's look at this picture here. This is a picture of a wire. The wire itself is a conductor. This is where we want our electrons moving within, right? We want current flowing here. But the insulator kind of encases it to keep it, well, let's just keep the electron flow within the wire itself. So moving electrons. Electrical current is made of moving electrons. Atoms stay fixed in place, right? The atoms aren't moving, the electrons are. So an atom and an insulator, a bound electron. An insulator, the electrons are tightly bound to the atoms and cannot move. Whereas a moving electron, right, an atom and a conductor of electricity, some electrons come free and can move to create electric current. Since electrons are negative, they move in direction opposite of the positive current. And last, so resistance of some common objects. The resistance of an object varies. Electrical devices are designed with a resistance that causes the right amount of current to flow when the device is connected to the proper voltage. So dry skin has a resistance of about 100,000 ohms, a very, very high resistance. Wet skin has a much lower resistance. Therefore, the same voltage will cause more current to pass through your body. So wet skin is actually very, very dangerous. Where dry skin, well, you're actually pretty safe. I'm not saying you want to run out and go get zapped by a lightning bolt, though.